Welcome to the Rich Report, a podcast with news and information on high-performance computing. Today, my guest is from Allinea. We have Mark O'Connor. He is a technical fellow at the company. Mark, how are you doing this morning?
Doing good, thanks, Rich. How are you?
Oh, great to have you on the show. You know, we've you and I have talked about performance reports before, but we're going to try to do some demo here and learn more about this product. So I guess why don't we start with that? What is the performance report product?
So, performance reports is a very simple, very low-friction way to give system administration staff, cluster owners, and application developers and maintainers kind of a really effective way to characterize the performance of their MPI applications. So this is to answer questions, okay?
Yeah.
Answer questions like, is my application sufficiently well optimized? Does it actually benefit from running at this scale? Or what's limiting the performance on this particular hardware configuration? Many people have got access to multiple clusters. It's not always clear where you get the best bang for buck or why, especially when you're looking at different kinds of architecture, for example.
Sure. And these users might just be scientists. They might not be computer scientists, right? They know these particular intricacies of these different architectures.
Well, this is something that's been kind of haunting us as a tools industry in HPC for quite a while now. And over the last kind of 10 years of writing debuggers, profilers, and tools for HPC, I've often struggled with this understanding. And it's like this HPC, you're working with some of the smartest people on the planet. It's one of the things I love about it.
Sure.
And 5-6 years ago, we come out with a tool that we think is quite a lot easier to use. It's very straightforward, and people say, it's I know I'm just going to use printf. And really trying to work out why this kind of reluctance to use a tool was coming from. And here we are a long way down the road, and it turns out that when you ask people and you sit down and work with people, what you see is everybody's using their full concentration and attention for solving a problem. Okay?
Yeah.
It might be a domain problem. It might be a particular bug they're trying to solve. They're thinking about the bug. They don't have a lot of spare capacity to learn a new tool or to interact with some other thing they haven't seen before or haven't seen for 6 months.
Yeah.
And it's not really about being too complex to use. It's got to be easy enough to use without thinking at all. Because all of that thought, all of that concentration is going towards actually achieving something.
Yeah. So something like this, instead of looking at a big memory dump, and trying to figure out what happened, they are used to browsing web pages. I mean, and sorting through charts and things. So you've kind of packaged this up very neatly.
Yeah, everybody can grasp a bar chart right away.
Mm-hmm.
And that's kind of half of it. A lot of the work and the effort that went into developing this particular product and making it simple was to make sure that on almost any system, you just add one command to your existing script or whatever.
Yep.
And this report is just generated automatically. There's nothing to configure. There's no GUI interface to use. In our demo today, we're just going to be looking at reports because there isn't anything else to see. It's that minimal. And we've been really surprised that when you make a very simple, very effective tool, people use it in ways that we never imagined. Even in the beta back in January, we had people using it to evaluate different clusters during procurement from vendors. We've already sold nationwide licenses, multi-site things, so people can run this as standard across multiple different systems.
Mm-hmm.
We've had people wanting to gate access to their cluster or to their production queue, demanding people produce one of these reports to show that the basic things like a regular car checkup or something, that this code is still built correctly, still optimized correctly, still performing well enough to be worth running at large scale, that kind of thing.
Mm-hmm.
It's been fun.
Well, this to me, Mark, looks like a great communication tool because I talk to these system administrators, right? And typically they're going to get bugged by the user. He's going to say, my application's running slow. And that's about the only information they can hand the guy. So he doesn't know where to start, right? Is it the file system, network? Is something broken? But something like this, you hand them, prints out this HTML with all this information, and he's got a roadmap to see what's going on in this particular use case.
Yeah, and like you say, communication, especially between the system support staff
Mm-hmm.
and the application developers and maintainers,
Yeah.
is so important, and often a real conflict point. There's always the system's broken.
Yes.
No, the system's fine. No, and
Yeah. Back and forth.
the last thing you want is to then have to take the system down to run like networking tests overnight or for an entire unscheduled maintenance period, and then to find nothing.
And there was nothing wrong.
And then your critical application's still not working.
Mm-hmm.
So something like this can really help to avoid getting into those situations unless it's really necessary. And we'll see an example of that in a minute.
Okay. Well, yeah, this is this just looks to me like it's so simple, right? I mean, adding the command at the beginning, and you get, here we got a new report, right? So,
Yeah.
Tell me what might somebody do with this particular one? Okay, it's just summary. It's CPU bound, right? So I know where to look in my code to manage that.
Well, let me take you through a couple of examples. So what we're looking at here is a kind of a fairly typical HPC code. It's CP2K, that's an open source molecular dynamics code.
Yeah.
Running at 256 procs, that's kind of fairly standard for this sort of configuration. And as you say, right away you can see it's CPU bound, but kind of barely. It's spending almost half its time in MPI communications, which you want to avoid. Green is good and blue is bad.
Yeah, okay.
If you're spending more time communicating than actually computing, you're not getting the best value for money out of your cluster.
Sure.
In this particular case, we can see a number of different things that this report would point you towards, thinking about what could I do to get more out of this code, or is this okay? The first advice is to look at the CPU performance.
Mm-hmm.
So we've got this breakdown of the CPU code here. And we can see we're spending, a lot of time, 60% of the time, just accessing memory. So this is very memory bound.
Yeah.
Now, whether that's acceptable or not depends a bit on the nature of the code. I mean, molecular dynamics is a much harder problem to solve scalably than something like linear algebra.
Mm-hmm.
So there's always a certain amount of communication that's necessary. But you could with something like this kind of most of the time you're just waiting on the memory. That's it's not getting. Maybe it's pointing towards you want a slightly different architecture for this. If you have the opportunity, maybe something with a high memory bandwidth would perform better for you, or maybe it's latency.
Yeah.
So you can run a profiler,
Yes.
something like map or Intel vTune to understand exactly why that's so high, whether you can do something about it.
Mm-hmm.
I mean, typically improving cache performance means restructuring your data structures, and that can become quite a large job quite quickly.
Sure.
So it's not always the first place to look.
It's also suggesting something about vectorized instructions. It's not spending much time there.
Yeah. So it's spending like 40% of its time doing numeric operations in total, but only 10% of its time on vectorized stuff. And this is something that Intel's beating this drum particularly hard, but it's true on every architecture.
Yeah.
That if you're not using the vectorized AVX SSE2 instructions, you're getting a fraction. We're talking a quarter or an eighth of the performance out of your CPUs.
Mm-hmm.
And if you look at moving something like Xeon Phi or offloading to a GPU, if your loops aren't vectorizing, you're completely yeah. And this is something that's generally very local, kind of a per loop optimization to do. The compilers aren't as good as people like to think at doing this automatically.
Yeah.
But they do give you a lot of helpful advice if you ask for it. So Intel's minus vec report would tell you which loops are vectorized, which loops are not, and why, and then you can dig in further. So this is basically telling you, hey, run something like map and find out which are the hot loops, and then see why they're not vectorized.
Yeah.
Sometimes a combination of simple compiler flags, like specifying specifically the right architecture, makes a huge difference to the performance.
Yeah.
And if you don't see a figure like this, then you don't know to do that. You could be leaving a lot of performance on the table, as this code at the moment is.
Yeah. Well, what's this about it's spending a lot of time in this MPI, the time in point-to-point calls, 91.8%. It's that's just doing the same thing over and over, what would you say?
Well, so generally you would know as the application author whether it's you would expect to spend a lot more time in point-to-point than collectives.
Yeah.
That in itself doesn't surprise me, but the rate, the rate of communication of 50 megabytes a second in those point-to-point calls. I mean, this is running on a Cray XE6.
Okay.
So that is nothing. That's
Yeah.
not your network bandwidth.
Right, right. I've spent a lot of money to get bandwidth in that Cray system.
Yeah.
Yeah.
And so what this is telling you is that your processors are spending most of the time in their MPI call just waiting for the other guy to be ready to communicate. A lot of synchronization overhead. And that's bringing this effective transfer rate right down.
Yeah, yeah.
And to some extent, you will always find that as you increase the scale, you spend more time communicating. But this is really showing that you've got your workload imbalance going on at some level here.
So, Mark, before performance reports came around, how would I derive this information? Would I have to run individual tools to look at these specific areas?
There are a number of options open to you.
Yeah.
So, yeah, you could run something like Intel VTune on a single core to get the CPU breakdown.
Yeah.
You could have run something like MAP or Scalaska or one of these kind of specialized Vampire trace to try and get the MPI details out.
Yeah.
Again, you could look at some kind of I/O profiler. So each of these is kind of giving you the headline figures that one specific tool would have given you before, but there would be a significant barrier for, okay, now I'm going to learn how to use this tool, I'm going to go on a course, I'm going to get it installed and set up correctly, and I'm going to put up with slowing my job down, I'm going to do a smaller scale. I mean, the point of performance reports is you can run it on your production jobs.
Yeah.
You don't need to compile especially,
And this gives you the big picture.
Yeah, but the the biggest improvement we can see on this anywhere is actually in this memory section in the bottom right here. The amount of node memory that's being used, the peak during the runtime of the job is 7%, which means that this particular data set is tiny, too tiny to run on like 16 nodes of this Cray XE6. So in fact, if you just ran it on, you could run it on maybe an eighth of the nodes.
Yeah.
Okay. Maybe just 32 processors instead of 256. All the data still fits into RAM. It'll take longer, but it won't take 8 times longer because you'll lose all of this MPI, all this communication time then will basically go away. So you can really, just by making use of the actual hardware layout you have on the machine, you can be much more efficient with your allocation. You can run more jobs.
Yeah. And diminishing returns, right? You throw the whole machine at it when it's not appropriate.
Yeah, and I guess this is something especially that the cluster owners and the administrators would care about most.
Sure.
Right? They want to make sure that their machine's being used to get as many results out as possible.
Well, let me ask you a little bit about performance reports. Is it does it care if it's a Cray or some other system? I mean, it's kind of agnostic, isn't it?
Yeah. So the set of figures we've chosen, we tried to make sure that we can get exact comparable figures on all the different architectures that we support.
Yeah.
Which is, again, for example, Cray have got their own tools, HP have got their own tools, and these are generally very good, but you can't use them to compare your different machines. And when you're collecting performance data and then you get a new machine or you run somewhere else, you can't then cross-compare to, is this still doing what I expect it to, or doing something different?
Yeah, in a production way.
Yeah.
Yeah.
As a comparison, check another example. This is this is HPL.
Yep.
So the Linpack benchmark, which everybody loves to hate these days, depending on which side of things you stand on.
Yeah. And I wouldn't expect any I/O, and there I see it's not doing it. And it's
It's not doing anything really apart from multiplying numbers really quickly.
Yeah.
In comparison to a real HPC code, you can see it parallelizes extremely well. Of course, it does. It's linear algebra, right?
Yeah.
Despite that, it's still not vectorizing very well. And this was just using GCC on the download from the website.
Yeah.
You could get a lot more performance out of it. And if you were benchmarking your cluster with this, you could see instantly that that's not the way to go. Again, the memory usage, we're seeing you could be running a much larger problem case here, and be getting better figures out. But it's not always about the code that's the problem. Okay,
Yeah.
here, this is also Linpack.
Yeah.
In fact, it's the same binary.
Yeah. So what
And
changed? What changed between the two?
that exactly, that's the same question any user would be asking
Sure.
him, saying,
Yeah.
I submitted 5 of these jobs overnight, and what the hell's happened to this one?
Right. Right.
Okay, and typically he'd go to the administrator and say, look, this one job took 8 minutes to run. The cluster's broken.
Yeah. Yeah.
And maybe there's some kind of networking issue, right? Some connectivity problem.
Yeah. Yeah. We went from
Well, I think-
92% efficiency on the CPU to 24.
Yeah, and we can see it's not that it's an unoptimized binary. That does happen because the CPU figures, if you watch as I flick between them a little bit, they're basically the same.
Yeah.
But the MPI is where it goes crazy. Now, we can see that all of the time, again, is now spent in collective calls. That's typically things like MPI barrier or scatter or gather, with a 0 bytes per second rate. So it's just synchronization. 75% of the time spent synchronizing. That's weird, certainly.
Yeah.
And the other clue comes from the memory report down here, saying there's significant memory usage variation. Okay, the peak process, which is 266. That's kind of the peak used by the largest single process.
Yep.
And that's like a huge amount. Some of them, in fact, most of the process is using a very small amount, which again suggests you've got a massive imbalance in the actual compute workload being shipped out here. And so this is suggesting that, okay, it's the same binary, but there's a massive imbalance in the workload. Maybe we should look at the input files.
Yeah.
And it turned out this actually happened to me completely by mistake while gathering a whole bunch of benchmark figures. I set up a batch script to submit all of these overnight. And of course, they were using the same input file. And my script overwrote the input file. So it started with 256 processes, but ran an input file for only 64 blocks of separable data. And it turns out Linpack will do that perfectly happily, but 3/4 of the processes just sit around doing nothing.
Yeah. Yeah. Interesting.
Yeah. So, I mean, I/O is also kind of a fairly hot topic at the moment.
Yeah.
And the sort of I/O figures, you see, this is just an example using MadBench. I think it came from CMB codes. They ripped out all of the logic, but it's supposed to be very representative of actual data reading, writing workload.
Yeah. Yeah.
This is running on a single Sandy Bridge node writing to the local hard disk for performance measurements. And just to see how it behaves when you start stressing it,
Yeah. Yeah.
Because when you stress an I/O file systems, very unusual things can happen you don't expect. And this, especially on large machines with very parallel file systems, it's not always clear where the contention's coming from. There's multiple levels of caching involved. It can get very confusing.
And that triangle that you guys use, your icon to see what's going on there. Very different picture from the Linpack here, right?
Yeah, exactly.
Yeah.
And that's easy if you're leafing through reports. You can kind of quickly see how that changes around, give you a simple overview of what's going on.
Sure.
It just reflects the same information shown in the bar chart.
Yeah. Very slick. And you're just flipping between tabs here of these different HTML reports as you do that. Yeah.
And this is the first version. At some point, we'll have a report that's got multiple bars from different reports on it, comparisons and so on. But even the poor man's comparisons flipping between gives you actually a very compelling understanding of what's changing between these things.
Yeah, because your eyes are designed to see difference, right? So it pops out.
I mean, one of the things we see as we increase the number of processes on this node is the amount of time. So initially, you've got all your time spent in I/O and CPU, very little in MPI. As soon as we increase the number of writers, so increase the contention, the amount of MPI time increases. That's not really expected.
Yeah.
And again, we've got this all the times in collective calls at a very low rate. That means there's kind of a load imbalance somewhere.
Yeah.
Now we're breaking up the data in the same way here, so we don't think it's a partitioning problem. Now when we look at the I/O section, we can see compared to the previous version, the write rates in this first version, for example, we've got 4 writers doing 330 megas a second each. That's 1.2 gigs a second. That's pretty good. There's certainly some caching going on in there. We can see we're not using all of the node memory, so a lot of that will be cached.
Yeah.
But when we increase the contention, that just plummets 70 megas a second. We're like double the writers. And this is very common when a file system is stressed. that the write performance just falls off a cliff. So read is very easy to cache and serve to lots of readers, but lots of writers it becomes more difficult.
Yeah.
And the reason we see the increased MPI level here is then because the writers are in contention with the edge of the disk, and some of them are finishing a lot later. They have to, kind of waiting. Some of them are finishing a lot later, and while they're waiting for those ones, the other ones are in MPI. So all of these things are kind of interlinked, and that's why it makes sense to look at one summary report that gives you all of this information in on one page, instead of being caught in, you're doing my MPI profiling silo. You could run MPI profiling this all day and not find out it's an I/O contention issue.
And then, Mark, when you're, is there a methodology? Like everything you said makes perfect sense, but you're a technical fellow at Allinea, right? Looking at this report, do I have to be an expert to really go in there and say, well, this indicates that, right? Out of these, all what we're looking at here, what's the recipe?
So we've tried to include these suggestions about where to go. So in stepping back a bit, there's always context to these numbers.
Yeah.
And that's something we've spent quite a bit of time on, trying to make sure that this context is generally helpful.
Yeah.
Even starting from very basic, 17% of CPU time, that is low. Look at I/O performance first.
Yeah.
Okay, I'll look at my I/O performance. Most of the time is spent in write operations with a low transfer rate. This may be caused by contention to the file system or inefficient access patterns. Use an I/O profile to investigate which.
Yeah.
So we're trying to guide you to the right area to look at.
Right.
And some users, the more experienced users, will say, okay, yep, right file system contention, I know where I'm going to look for that. Other people, they might say, okay, I don't know, but I've got this report.
Yep.
I'll take this to our support specialist or our support team, say, hey, I've got this report. Is this right contention? Can you help me with this? Which is a huge step forwards, instead of saying, my job's taking a really long time today. Is the disk broken again?
Yeah, yeah. And here's 200,000 lines of code. Go tell me what's happening.
Fix it, monkey.
Yeah. Right.
So it's trying to take that conversation to a higher level, I guess.
Yeah, absolutely. Is there a way to to kick the tires on this, and for people to try it out, or how does the license work?
So all of these examples you can download from our website. They all come with explanations of how or what we read into them and how you can read into them too. Yeah. You can also, as you say, just download it and kick the tires. There's a free, I think, 15-day trial. Just grab it, download it, give it a go. It's very easy to get started with. And you can run it on your laptop or on the cluster. You don't need root access. You don't need to configure PAPI. You don't need to set anything up. You just extract it, run, get some figures out.
Yeah. Well, it's great that you have these different ways to communicate the information, because somebody might just be running into Amdahl's law here or something, and it looks like Performance Report is very smart about where it's pointing you in the areas to look at.
Yeah, there's always places to improve, and we'll keep on trying. But I'm very proud of where we've got so far with this.
Well, terrific.
And people love it, so I'm really happy.
Yeah. I mean, you really packaged it in a way that's accessible, and I think this is a great step forward. Yeah,
well, like I say, we're all far too busy to be using complex tools to get out.
Yeah. Well, congratulations on this, Mark, and I want to thank you for coming on the show today.
Thank you, Rich. It's been a pleasure. Anytime.
You bet. Okay, folks, that's it for the Rich Report. Stay tuned for more news and information on high-performance computing.